Slow sand filtration has been used to produce clean drinking water since the early 19th century, and SSF systems are still in use worldwide, including in major cities like London. The technique uses a bed of fine-grained sand to filter out small particles, including some naturally occurring organic materials, reduce turbidity, and remove many pathogens. One of SSF's greatest strengths is its simplicity. It requires few chemicals, uses minimal energy, and has a low carbon footprint, making it an eco-friendly solution. But space and operating requirements mean SSF systems have fallen out of favour in recent decades to be replaced by more intensive systems. Now, new research on the interaction between biology and engineering is pushing SSF technology forward, addressing some of its limitations and unlocking new potential. In SSF, a layer of organic and inorganic material, known as the Schmutzdecke, builds up on the sand-water interface. This layer is essentially a biofilm, a complex community of microorganisms that thrive on the surface of the sand and play a crucial role in breaking down contaminants. While the Schmutzdecke performs the water treatment, it also slowly clogs the filter and reduces water flow. Traditionally, this problem has been managed by draining and manually cleaning the sand beds, a laborious process that involves taking the entire filter offline. It also disrupts the sensitive biofilm community, requiring several days to bring the filter back into routine operation. This is where recent engineering innovations come in. Underwater skimming is a new technique that uses a remote-controlled machine to clean the Schmutzdecke without significantly disturbing the filtration system, allowing the microbial ecology of the filter to be preserved and brought back online more rapidly. This reduces downtime, increases overall water production, and improves water quality. Recent research also shows some microbes in the Schmutzdecke can degrade certain pesticides and pharmaceuticals that are challenging to eliminate using conventional water treatment methods. By preserving a diverse and active microbial community and optimizing conditions like nutrient availability and oxygen levels, we can enhance the removal of these micropollutants. These simple engineering interventions interact seamlessly with the biological processes at work in SSFs, creating a more effective water treatment system and optimizing a low-cost, sustainable solution to emerging water challenges to enhance public health resilience at both large and small scales worldwide.